This is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I am going to deal with the course Computational Aerodynamics. And today's topic we will see finite difference method with the first order and second order methods. Okay, so already we had seen what is CFD and what are the steps involved in the CFD, what are its applications, and then after we had seen a grid, okay, and mesh, uh, structured grid, unstructured grid, okay, and a uniform and non-uniform grid. So we had covered in the lectures, okay. So these are the applications, and this is a grid. So we had seen. So this finite difference method we are applying at the grid points. If you see, so these are their grid points, okay. So as I told you, so this is nothing but boundary points. So this entity is nothing but boundary. So this entity is nothing but the boundary. So these are the boundary points, and the remaining points which are present in the domain are called interior points. Basically, these are called internal points or the interior points. So the grid points are obtained when the intersection of x and y lines occurs. So in the case of structured grid, so these x lines will travel or will have a parallelity, and y lines are also have parallelity, where the intersection of these x and y lines will give rise to a point called grid point, or it called a mesh point, or it is a node. Okay, so there are different naming phenomena, and here this entity is called cell, which I have discussed. For the case of structured grid, which is 2D, so basically this is called a quadrilateral cell, so which is made up of 4 points here. So 1, 2, 3, 4. Okay, and this is called the cell face. Okay, in the case of 2D, it is called hexagon. Okay, so and here the number of cells and the number of grid points depend upon the points which we will assign on the x-axis and points which we will assign on the y-axis. Okay, so if it is 3D, x and y and z axis. Okay, so already like we had seen that the finite difference method is applied at the grid points. So what we do, we solve the governing equations at particular grid points and convert this governing equations, which are in partial differential form, to a discretized form. Those discretized form equations will be actually made set of linear algebraic equations, and we will collect in the form of matrix and invert it. So this is what a general CFD method is done for finite difference method. Okay, so we had seen non-uniform and uniform grid both along x and y axis. So coarse grid, finer grid we had seen, and unstructured mesh and its example. So types of fluid flow element, and now we will be seeing actually finite difference method. So already I have introduced you. So what is finite difference method? So let's take a mesh. So already we had seen the mesh figure in the previous slides. So I am actually drawing here a detailed view. So let's say here this is our point of interest. I am taking a particular area in the mesh, okay, and I am taking particular point. So this is a point, and this is another 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 point. Okay, so if we call this point as I comma j, so what would be this point? I told you. So I plus 1 comma j. So this one it would be I minus 1 comma j. So this one it would be so I comma j minus 1, and this one it is I comma j plus 1. Okay, so basically what we are writing is like, so this is x-axis and this is y-axis. So we are taking the convention like x-axis as index I and y-axis as index k, sorry, index j. So y-axis as index j and z-axis as index k. Okay, so you have I, j, k. So since we have only 2D, so therefore we have index I comma j. Okay, so we have only I comma j things. So for the forward difference, we need to see the terms I plus 1 comma j and I comma j. So already I told and I explained in the previous class. So for the forward difference fd, so these terms are involved: I plus 1 comma j comma I comma j. These terms are involved. And for the backward difference, so we have I comma j comma I minus 1 comma j. So I'm talking the variation on like along x-axis along item. So for the central difference CD, so you have so I plus 1 comma j and comma I minus 1 comma j. Okay, so these are the terms like which are involved in the forward, backward, and central differences. Okay, so basically these things are important while calculating the fluid flow properties at the particular grid point. Okay, so when we are solving when you are iterating it, so we will give the index notation and solve it. So that's why we are giving the index notation for the uh, finite difference methods. And how we solve is like we will actually discretize, or we will change this partial derivative in a discretized form and arrange in a set of algebraic equations and invert it. Okay, so here we will see, so basically how this formula has obtained. So finite difference method, finite forward difference method, backward difference method, and central difference method. So we will be seeing their small derivation. Okay, so everything has started with the Taylor series of expansion. So here you can see this equation 1, so which is of Taylor series of expansion. So if you want to calculate the value, so f can be like a velocity. So here the f can be so u velocity, v velocity, w velocity, pressure, temperature, density, anything. So flow parameters. So in order to govern any fluid flow, so you should estimate what are its fluid properties. Okay, so you should describe what are its properties. So first, we should know what is its velocity, what is its temperature, what is its pressure, and density. So these things you should be able to describe. Okay, so here if you see the Taylor series of expansion, so f of x plus delta x. So here the meaning is, so the x is nothing but, let's say it's an initial position. Okay, so x, already we have seen that x is nothing but it is I, and this is index notation terminology, so which is nothing but the initial position, and delta x is nothing but the change. So if you make it as x minus delta x, it is the negative change or backward. So x plus delta x, it is change forwards. Okay, since it is one time, it is 1 delta x. So if you have x plus 5 delta x, it is 5 times the forward change. Okay, so this is what we have, right? So now we will be seeing actually using the Taylor series of expansion, how do we get the forward difference, how do we get the backward difference. Okay, so we have f of x plus delta x. The formula for the Taylor series, like you have, so f of x plus dou f by dou x into delta x, and dou square f by dou x square into delta x square, and so on. So the next term would be dou cube f by dou x cube into delta x cube by 3 factorial. So this is what the Taylor series has. So on dou power n f by dou x power n delta x power n by n factorial. So this is what we have. So from the Taylor series of expansion, so how many terms that you consider is very important, and the consideration of these terms will give rise to the order of accuracy of this cube. Okay, so we will see here what is this. So what we are doing is like, so this equation 1, we are replacing, how we are replacing, we are replacing this x as I, delta x as 1. Okay, and we are writing in the subscript form. Instead of writing in this form, so we are writing in subscript form. So what is happening here is, so the f of x plus delta x is written as, so the f as I told you, if you are calculating, it would be velocity, it would be pressure, it would be density, it would be temperature. So here this f is like u, so the x already I told you, which is I, plus delta x is nothing but 1. Okay, so if you are having the change along x-axis only, then we are writing x plus 1 comma j. Okay, so instead of writing in this way, so we are writing in the subscript manner. Okay, so this f of x plus delta x term, so we are writing it as, so this f will be written as u, so x is written as I, so plus delta x it is written as 1. Okay, comma j. So there is no, so since we are dealing with I plus 1, so for a constant j, so that's why we have j. Okay, so next f of x is written as u of I comma j. Okay, so if you have variation along x-axis only, then the I term will vary. If you have variation only along y-axis, you will have only j term. If you have variation both along x and y-axis, then you have variation of I comma j. Okay, so if we apply this concept here, so what happens is like, so here the u of I plus 1 comma j, what we write is f of x plus delta x. So for the constant y term, which is j, so this f of x is written as u of I comma j, so plus dou f by dou x, which is, so the f is written as u, so therefore dou u by dou x at I comma j. So we are actually finding out, so what is the value of velocity at the next time level or next point. Okay, so this value of velocity at the next point depends upon the initial point and its derivatives. So this is what we have. Okay, so here what we are finding is this point. So at this point, what is the velocity? Okay, so what is its velocity? It is calculated by the Taylor series of expansion here. So velocity at the next point is function of the initial point and the derivatives at that particular point. So here you can see the terms dou u by dou x at I comma j into delta x. So dou square u by dou x square into delta x square by 2 factorial. So dou cube u by dou x cube at I comma j, so delta x cube by 2 by 3 factorial. So that's why you have 6. Okay, so this is the concept of Taylor series of expansion. Now, so in the continuity equation, you have the terms dou u by dou x and dou v by dou y plus dou w by dou z. So these terms are there. So in order to replace these terms in terms of this Taylor series of expansion, so in the terms of index notation, so what we do, so we take here in the equation 2, so dou u by dou x term one side and what is it, and shift all the terms on the other side. So this is what we have in the 3. So dou u by dou x at I comma j will be equal to, so u of I plus 1 comma j minus u of I comma j divided by delta x. Okay, so this equation 2 would be like how, so dou u by dou x into delta x is equal to, so u of I plus 1 comma j minus u of I comma j and the minus remaining terms what we have. So if we divide by delta x, so then you get, so u of I plus 1 comma j minus u of I comma j divided by delta x. So this is nothing but the forward difference term. Okay, so this is what we have, the forward difference term, and the remaining term, so which we are neglecting. Okay, so these are called the truncation error. Okay, so if we want to find dou u by dou x, what we do, so in the Taylor series, by the using of Taylor series of expansion, so we are shifting the terms to other side and we are getting what is dou u by dou x. Okay, So that would give you u of I plus 1 comma j minus u of I comma j divided by delta x. So when you divide by delta x, this delta x square would become delta x. This delta x cube will become delta x square by 6y. Okay. So if you are neglecting these terms, so this is called the truncation error, and the order of accuracy is called the first order in space. So here you can see you have the delta x term. Okay. So the delta x term is nothing but the leading error term. So the term which you are leaving in the derivation is nothing but the leading error term. So that's why we call it as the first order accurate in space. Okay. So that's why we call it as first order accurate in space. Fine. So this is what you have the forward difference. Similarly, so what you have if you want to get the backward difference. So how do you do it? So we will write down here f of x minus delta x. So which would give you f of x. Okay. So next minus dou u by dou f by dou x into delta x plus dou square f by dou x square into delta x square by 2 factorial plus dou cube f by dou x cube into delta x by 3 factorial. So this so on terms are there. So for the backward difference, what we are doing, instead of using f of x plus delta x, so we are using x minus delta x. Okay. So what happens here? So we need to find the backward difference of first order derivative. So basically this first order derivative dou f by dou x, or what we say dou u by dou x term, can be evaluated in 3 ways. So one is like forward difference, backward difference, and central difference, and the order of accuracy can be improved by doing other methods. Okay. Now we will see what is the order of accuracy for the backward difference. So for the backward difference, what we are doing, we are replacing this. So initially we have f of x plus delta x. This plus delta x is replaced as minus delta x. Okay. So this is the truncation error term. Okay, we will neglect this. So what we have? So minus dou f by dou x into delta x is equal to f of x minus delta x minus f of x. So finally what it would be? So plus truncation error term, TE term. So this is called. So therefore dou f by dou x will be equal to f of x minus f of x minus delta x divided by delta x plus truncation error term. So this is the formula for the backward difference method. Okay. So this is the formula for the backward difference method. So what it would be? So we can write this one dou f by dou x as, so dou u by dou x. So at what point I comma j, the backward difference will be equal to, so u of I comma j minus u of I minus 1 comma j divided by delta x plus order of accuracy of delta x. So this is called O of delta x is nothing but order of accuracy. So which is of first order accurate. Okay. So this is what we have. So till now we had seen how we have obtained the backward difference and forward difference. Now we will see how we obtain the central difference. So what we have here, so f of x plus delta x is equal to, so we have f of x plus dou u by dou x into delta x plus t term, truncation terms. So f of x minus delta x will be equal to f of x minus dou u by dou x into delta x. So we will write the term here plus the truncation term plus truncation term. So we have this equation. So in order to get the central difference for dou u by dou x, what we have to do? We have to subtract this. Okay, equation here 1 and equation 2 subtract. So what happens? So this would give you f of x plus delta x minus f of x minus delta x, which would be, this will get cancelled. So plus 2 times, okay, so dou u by dou x into delta x plus the truncation error term you will get. Okay, so this is what we have here. Fine. So finally, what is the formula of dou u by dou x? So of for central difference. So that would give you, so u of I plus 1 comma j minus u of I minus 1 comma j divided by 2 delta x. So this is what you have. Okay, but here the order of accuracy would be delta x square. Why? Because so when we are subtracting it, the odd term, the even term will get cancelled, the odd term will remain. So that's why you have the order of accuracy of, so order of accuracy of delta x square. Okay, so we will see in terms of u terminology. No worry. So what we have here, you have I u of I comma, sorry. So u of I plus 1 comma j will be equal to u of I comma j plus dou u by dou x into delta x, which is at I comma j, plus dou square u by dou x square into delta x square by 2 factorial plus dou cube u by dou x cube into delta x cube divided by 3 factorial. So this is what we have. So similarly, so u of I minus 1 comma j will be equal to u of I comma j plus 2u by, sorry, this would be minus dou u by dou x into delta x, which is I comma j, plus dou square u by dou x cube into delta x square divided by 2 factorial minus dou cube u by dou x cube into delta x cube divided by 3 factorial. So here what we are doing, we are subtracting. So this by this. So when you do subtracting, what happens? So this minus and minus will become plus, this will be minus, and this will become plus. So this term will get cancelled, and this term will get cancelled. Okay. So what happens here? So the final term would be u of I plus 1 comma j minus u of I minus 1 comma j is equal to 2 times dou u by dou x into delta x, okay, and plus 2 times dou u by dou x dou cube u by dou x cube into delta x cube divided by 3 factorial plus so on terms. So if you sum these terms here, then what will we get is like the second order accurate scheme. Okay, so here we can see what it is coming. Okay, so here you can see what we are doing. So you need to get dou u by dou x. So this one dou u by dou x will be equal to, so u of I plus 1 comma j minus u of I minus 1 comma j divided by 2 delta x. So this is what we have. Okay, so minus dou cube u by dou x cube into, this would be 2 times into delta x cube divided by 3 factorial into 1 by delta x. So this is what we have. So here the truncation error term, what we have is like delta x square. So therefore the central difference scheme is second order accurate in space. Okay, so what I want to say is that, so whether you take the first order, like the order of accuracy, which is of delta x square, delta x cube, so the leading term which is remaining is nothing but the order of accuracy of the scheme. Okay, so even in the first order scheme, you can actually increase the order of accuracy, or like when you replace the other terms. Okay, and here in the central difference also you can go for higher order terms replacing those things. so that you can calculate the values for the higher order accurate. Okay, so till now what we had seen is like in order to replace, so why we had done dou u by dou x or dou f by dou x? Why? Because in most of the places, so let's take the continuity equation, which is dou rho by dou t. So already I told you this time term we'll be writing like this: n plus 1 minus n divided by delta t. So this is how we write. Okay, at a particular point. Okay, and here you have, so in the continuity equation, what we have? So dou rho by dou t plus dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So whatever the process that we have seen for dou u by dou x, so similarly this process will be done for dou v by dou y, and similarly this process is done for dou w by dou z. Okay, so for these things we actually implement these methods. So the main intention behind to replace these partial derivatives using Taylor series expansion is we can replace the first order terms of the governing equations either in forward difference or backward difference or central difference to get an accurate solution using CFD. So this is what we are doing. Okay, so now in the momentum equation, so we have a term which is a second order derivative term. So we have mu into dou square u by dou x square plus dou square u by dou y square term. So this is what you have actually. So we should also replace this dou square u by dou x square term. So what I am saying is that we can replace the first order derivative terms in the governing equations. Now how to replace this second order derivative terms in the governing equations? So we will see now. So previously we had seen for the central difference. So what we have done? So u plus 1 u of I plus 1 comma j. So this term minus u of I minus 1 comma j. So this term. So we have done to get the central difference for the first order. If we add these two, then we will get the second order derivative terms. So we'll see here how we will get. Again we'll write here. So u of I plus 1 comma j will be equal to u of I comma j plus dou u by dou x into delta x at I comma j plus dou square u by dou x square into delta x square divided by 2 factorial plus dou cube u by dou x cube into delta x cube by 3 factorial plus so on. This is what we have. So what is I minus 1? U of I comma j minus dou u by dou x at I comma j into delta x plus dou square u by dou x square into delta x square divided by 2 factorial minus dou cube u by dou x cube plus so on. So here when you add these two terms, what we have? So our this odd terms will get cancelled. So when you subtract, your even terms will get cancelled. Here odd terms are getting cancelled. Okay, of the delta x. So what do we have finally? So u of I plus 1 comma j plus u of I minus 1 comma j will be equal to plus 2u of I comma j plus 2 times dou square u by dou x square into delta x by 2 factorial plus the term next term would be so power 4. So this is what we have. Okay, so if we take these terms this side, so what happens? So finally, so the equation what we have is like, so dou square u by dou x square term at I comma j will be equal to So u of I plus 1 comma j plus u of I minus 1 comma j minus 2 u of I comma j divided by, so what is the order of, so this one divided by delta x square. Okay, and this one also it is like second order accurate actually. Okay, so here when you see the first order derivative term, so for the first order derivative term, so you have only two terms involved, which is u of I plus 1 and u of I, which is of backward difference, central difference, forward difference. And for central difference also you have I plus 1 and I minus 1. Whereas for the second order derivative term, you have three terms involved. So you have I plus 1 comma j term, you have I minus 1 comma j term, you have I comma j term. Okay, the order of accuracy is delta x square. Okay, now for the next, so the mixed derivatives. So the meaning of mixed derivative is like you can see, so dou square u by dou x dou y. So this term, if you actually what if you subtract this dou u by dou, so dou u by dou y minus dou u by dou y at I minus 1 for the central difference over 2 delta x. So this is what we have the mixed derivative. So we know what is dou u by dou y and we know what is dou u by dou y. This is I plus 1 comma j and this is I minus 1 comma j. So if you substitute these terms, then you will get the mixed derivative terms. So here, if you have mixed derivative terms in your governing equation, then we will be replacing these terms actually. So in general, to say for the finite difference method, so what we have is like in the equations, if you have the first order terms only, then you will approximate using first order methods. If you have the second order or the dou square u by dou x square terms, second derivative terms, then you will replace those terms with the this dou square u by dou x square terms. Okay, so here you can see basically we have written u of I plus 1 plus u of I minus 1. So these these are like linear form. So now, sorry, these are discretized form. So whatever we have written, the equation, it is written in the discretized form. So we'll arrange these equations at all the grid points. Now we have done only for I comma j. So in the computer, in the iterative method, this I will vary from 1 to n grid points and j will vary from 1 to n grid points. So if you have 100 grid points, then I will go from 1 to 100 along x. So if you have 100 grid points along j, so I will go from 1 to 100. Okay. So if you have in total, if you have let's say 150 or 190 grid points, so total you have 190 equations. So those equation coefficients actually, so what we do is like at the end, we will put in this form, which is like ax is equal to b form. Okay, so a is nothing but this coefficient of these indexes. Okay, so x is nothing but u of I comma j, u of I plus 1 comma j, so u of I minus 1 comma j. So these terms will be there. And b, if it is equal to the source terms, whatever we have. If you have any source terms, we can apply that. Okay, so this is how actually we solve the finite difference method for the first order and the second order methods. Okay, so in the coming lectures we will be seeing so what are the classification of partial differential equations actually. So when and we can mix up like how do we solve for the convection problem, diffusion problem. Okay, so in the momentum equation you have the convection term, so which is of u into dou u by dou x, and you have the diffusion term dou square u by dou x square term. So these terms, how do you specially treat it, and how do we apply this finite difference method, and how do we get these things? We will see. But before that, we will write a general second order PDE equation. Okay, and we will classify different types of equations. Okay, so like elliptic, parabolic, and hyperbolic, and how this classification is impacting the solution of the flow field and how it is depending on the Mach number, and how it is categorized, and where what are its application for the real world problems, and how do you classify these problems, we'll be seeing in the next class. Okay, thank you.
Like, share, and subscribe. Hit the bell icon for more updates.